Alright, so in class on Wednesday, we had discussed Thevenin equivalent circuits, and we said that using this voltage divider here, we can find the Thevenin equivalent by doing two things. The first would be finding the open circuit voltage here, which we say is either VOC or VTH, the Thevenin voltage. And in this case, between these 2 points, so whenever we do circuits and talk about Thevenin equivalents, we need to talk about between 2 points in the circuit, so two specific points or terminals or nodes in the circuit. When we consider a Thevenin circuit, it's between those specific points. So to find the Thevenin voltage, all we do is we take a measurement, or we calculate what the open circuit voltage is across that resistor right there. And in this case, we've already derived the voltage divider equation, which says that because these two resistors are each 1K apiece, that means that the voltage at that one on the right-hand side there is going to be simply half that of the source voltage. So in this case, the Thevenin voltage is equal to 5 volts, and that just comes from 10 volts times 1K times 1K, oops, not times 1K, sorry, 1K divided by 1K plus 1K. And that's equal to 5, of course. So then we try and figure out what the Thevenin resistance is. And to do that, we simply replace any batteries in the circuit with a wire. And so in this case, I'm going to redraw the circuit with a wire in the place of that 10-volt battery. And then we want to find the resistance between the two terminals that we care about. In this case, these two are in parallel. You can see that this one, if I slid it down here, would actually be would look very similar to a parallel circuit that we've seen before. But the key, of course, is that both sides are connected to each other on that. So in this case, when you have two resistors in parallel like this, they have a resistance, total resistance of half of each of their values when they're the same resistor, which means that the Thevenin equivalent resistance is equal to 500 ohms, or 0.5 K. So what I wanted to do in class on Wednesday but didn't get enough time to do was to look at what happens when we place a resistor in or as a load on this circuit. So you notice I've placed a 10K resistor as a load on this circuit. And I mean, when I say load, I mean it's just a resistance between the 2 points that we were considering before. So now what I wanted to do was to actually calculate, well, what is the voltage across that resistor? And I wanted to compare it then to the Thevenin equivalent to in fact show that they are equivalent. So in order to find the voltage across these two resistors, or excuse me, across that 10 ohm resistor here, so again we're trying to find what the voltage is across that resistor, we need to first collapse these two resistors together because they are in parallel, and to do that we can just simply redraw the circuit like this, and then we need to figure out what this value is. So in this case, this would have a value of 1K times 10 ohms divided by 1K plus 10 ohms, which in this case is 9.9 ohms. Then when we go through and do our voltage divider circuit, again this one is 1K, we will find that the voltage across this now, which is the equivalent resistance of those two, is 10 volts times 9.9 ohms divided by 1K plus 9.9 ohms, and that is equal. And the answer for this is 0.098 volts, which does illustrate, again, that when we place a load resistor that's much smaller than either of the resistors in a voltage divider, as we did up here. So this 10 ohm is much, much smaller than either of these 1K ohm resistors. We load down the voltage divider, and the voltage is not in fact 5 as we'd expect before, but in fact it's much, much less than 5. But now, if we take a look at drawing our Thevenin equivalent circuit and do the exact same thing, our Thevenin equivalent was a 500 ohm resistor and a 5-volt battery. And now we're going to actually place that same exact load resistance of 10 ohms across there. Now this circuit is much simpler to analyze because now all we have to do is just jump right to the voltage divider equation in the first place. So then we end up with doing 10 ohms. Again, the voltage we're trying to find is that voltage between those 2 points there. So 5 volts times 10 ohms divided by 500 ohms plus 10 ohms This is 0.098 volts, just as we got with the original circuit, but have noticed that we've used the Thevenin equivalent instead. And you'll also note that this is probably going to be a lot simpler when we start to have networks with tens of resistors in them. We collapse those down to one single Thevenin equivalent, and this calculation becomes much easier.